Welcome back everyone. In this lecture we will continue to define some basic notions in representation theory like indecomposable, decomposable representations. So, let me start with the definition of decomposable representations. So, we call a representation is decomposable if it is actually isomorphic to direct sum of two representations. So, let me just let V be a representation of A and we call V a decomposable representation if V is isomorphic to direct sum of two non-trivial representations. So, we just assume that all the representations that are involved here they are all actually non-trivial. Okay. So, the indecomposable representations, so they are the non-zero representations which are not decomposable. So, that means they are not isomorphic to a direct sum of two non-zero representations. So, we call V. So, to begin with indecomposable representations we just assume to be non-zero. So, we call a non-zero representation V indecomposable if it is not decomposable. So, that means if we have V isomorphic to W1 direct sum W2, then we expect that either W1 is 0 or W2 is 0. So, we already seen that indecomposable T invariant subspaces they played important role in linear algebra. So, they are going to play important role, continue to play important role even in representation theory. So, to emphasize that, first let me just prove a very important theorem. So, it is again as easy as what we did for invariant spaces, but anyway it is important to record this theorem. Let me just record it. So, if we take any finite dimensional representation of A, so that is going to be isomorphic to a direct sum of indecomposable representations of A. So, once we put this assumption that given representation is finite dimensional, then we can always make sure that that representation is always a direct sum of indecomposable representations. So, let me state it, any finite dimensional representation of A is isomorphic to a direct sum of indecomposable representation. So, this statement more or less follows from the definition. So, the proof again goes by induction on the representation. Okay. So, let us just quickly recall the proof. So, let us say V is the given finite dimensional representation. So, this is the given finite dimensional representation of A. So, now to begin with, if V is indecomposable, then there is nothing to prove. For example, if it is 0, again there is nothing to prove, or dimensional 1, then it must be indecomposable again we do not have anything to prove. So, we can assume that it is decomposable and has dimension at least 2. So, if V is either 0 or indecomposable, then there is nothing to prove. So, assume that V is decomposable and the dimension of V is at least 2, because if it is dimension 1, then it is easy to prove that it must be indecomposable. So, we can write V as W1 direct sum W2, or it is isomorphic to W1 direct sum W2 as representations of capital A. So, if you think about it, if you can actually have V is isomorphic to sum of 2 representations, direct sum of 2 representation, then it can be proved that by pulling back the copies of W1 W2 to V, then V must be a direct sum of 2 sub representations of capital V. So, that is something easy to prove, maybe I will leave it to you to think about it. So, now we have assumed that V is isomorphic to W1 direct sum W2. So, since we have assumed that both W1 is non-zero and W2 is non-zero, because V is not indecomposable. So, we should have this condition. So, then that would imply immediately that the dimension of W1 is more than 1 and strictly less than dimension of V, and similarly the dimension of W2 is also more than 1 and strictly less than dimension of V. Now, since both W1 and W2 are finite dimensional representations of capital A and both of them have dimension much less than dimension V. So, now we can use induction on the dimension, and then we will get that both W1 and W2 they are isomorphic to a direct sum of indecomposable representations of A. So, now it is easy to prove that V must be a direct sum of indecomposable representations of E. So, that just follows from the following exercise. So, if you know that W1 is isomorphic to direct sum of representations, let us call it V1 direct sum etcetera direct sum Vk, and then W2 is isomorphic to direct sum of representation, let us call it V1 dash direct sum etcetera direct sum Vr. So, if this is true as representations of capital A, then from this we can conclude that W1 direct sum W2 must be isomorphic to the direct sum of respective copies V1 direct sum Vk and then direct sum V1 dash direct sum etcetera direct sum Vr dash. So, from this exercise it is very clear that V must be isomorphic to these direct sum of Vi's and Vj dash. Now, since each individual Vi's and Vj dash they are all decomposable. So, we get a direct indecomposable decomposition of this capital V. So, basically this result guarantees that any representation, any finite dimensional representation can be written as direct sum of indecomposable representations. So, this actually immediately raises the following questions. Okay. So, the question 1 now will be, what are the indecomposable representations? Then the question 2 So, we have obtained this decomposition of any finite dimensional representation as direct sum of indecomposable representations. Okay. So, given finite dimensional representation of A, so that is going to be isomorphic to direct sum of some finite dimensional indecomposable representations of A. So, now we can ask this question whether this expression is unique or not. So, what does it mean? So, can we write V as direct sum of some other indecomposable finite dimensional representations of capital A? So, more precisely, can it be isomorphic to V 1 dash direct sum etcetera direct sum V r dash? So, mostly we want to actually have some uniqueness here. We do not want something being like direct sum copies of two different set of representations of capital A. So, for example, if you recall, so maybe I will come to that later when I talk about some example of representations. But now, so the question at least makes sense. So, we know V is indeed direct sum of indecomposable representation, whether the components that are involved in that direct sum, whether they are unique or not. So, that means first of all the number of components, whether they can be equal or not. So, we can ask this question whether k is equal or not, and once we know k is equal to r, then the components that are involved, whether they are unique or not, of course up to isomorphism, then we can expect, okay, is there any, in case k equal to r, is there any sigma in a on this r letters 1 to r from the symmetric group S r, such that this V I isomorphic to V sigma I dash for all I from 1 to r. So, this is actually something about the uniqueness, and most of the time this uniqueness is actually hard to prove, but we will see at least for certain algebras. Okay. So, this uniqueness is there. So, definitely for representation that are coming from finite groups. So, we will have this uniqueness. So, these are somewhat most important questions that one wants to address in representation theory. So, we will see at least how to address these questions for the group representation theory. Okay. So, this actually motivates one to actually focus on indecomposable representations, but let us try to understand like how this is going to help us. So, we already seen in basic linear algebra that if we are interested in finding this Jordan normal form or Jordan canonical form. So, we wanted to write V as indecomposable T invariant subspaces. So, that actually indeed helped us to obtain the Jordan blocks that we were interested in obtaining. So, but what is the relationship between these invariant subspaces and the representation? So, let us see that. So, that is what actually kind of motivates us to study the general representation theory. So, for that purpose, just for the motivational purpose, let us focus on this particular algebra, which is the one variable polynomial algebra. So, now, so let us go back to the question that we were actually interested in. So, we started with a matrix capital A and then considered a linear transformation associated with that, and then we were actually looking for a coordinate system in which we wanted to write that matrix or that corresponding linear transformation as simple as possible. Okay. So, what we did, let us go back to the original question. So, we started with the matrix n by n matrix, and then we defined this linear transformation T A of x equal to A x. So, this is defined on C n. So, then we were looking for a coordinate system. So, we are looking for a coordinate system. So, that means a basis B such that the matrix of T A B looks as simple as possible. So, now the question is, so what is the relationship with representation theory? So, if you think about it, so we actually translated this problem more abstractly. Instead of just looking at only the operator T A, we can actually take any operator T from endomorphism of V, and then we can just work with that linear transformation T. So, then we asked, is there any basis? So, with respect to that basis, the matrix of T looks somewhat simpler. So, because we already knew that the matrix of T A with respect to the standard basis going to be the matrix that we started with, and if we change the basis, the corresponding matrix representation of the linear transformation, they are going to be conjugate. So, that is why, so we were interested in looking for the basis on which this T acts as simple as possible. So, now we can actually just translate this in the language of representation theory. So, once we are given this linear transformation T, what we can do? We can immediately define this representation rho T. So, which is a map from C x to this endomorphism of V given by this evaluation x goes to T and 1 goes to 1. So, now we got a representation of this algebra C x. So, V can be treated as C x. Now, we can see that in terms of this representation language, the sub representations of C x, so they corresponds to T invariant subspaces. So, this is the connection between the representations and the T invariant subspaces of capital V. So, now once we have translated like this, so then using this previous result, so that is again written in terms of the representation language. So, that indeed says that any representation can be written as direct sum of indecomposable representation. That means, this V can be written as direct sum of indecomposable T invariant subspaces. So, this each EVI is going to be indecomposable subrepresentation of C x, which is same as indecomposable T invariant subspace. So, that is why like we can see that writing a representation as direct sum of indecomposable representation gives us lot from the application point of view. So, let us try to understand this correspondence very well. So, for that let me recall first of all what is the Jordan block. So, recall the Jordan block which is given by the matrix Jordan block matrix, but anyway let me write it in terms of the operator. So, given lambda in C and n greater than or equal to 1, we define the corresponding Jordan block which is an operator on this C n. So, which acts as follows. So, you have the basis E I, then the j lambda n acts on E I as lambda E I plus E I minus 1. This is for I greater than or equal to 1, and when you take E1, then you get just lambda E1. So, basically E1 is an eigenvector corresponding to the eigenvalue lambda. So, then if you take this basis E1 etcetera En, then it is clear that the matrix of this Jordan block operator is going to look like the Jordan block matrix, which has on the diagonal lambda and then the first off diagonal upper off diagonal will be 1. So, I have slightly changed the notation, so that I am having upper triangular matrix, but anyway there is no big issue, they are all conjugate, upper triangular and lower triangular Jordan blocks are conjugate. So, here we can see that now given linear transformation. So, I am just rewriting whatever results that we know in terms of the representation language. So, now we have this operator T which comes from the endomorphism of V. So, we know that there exists a basis of this capital V such that the matrix of T with respect to that basis looks in terms of the Jordan normal form. So, if you want to write in terms of these operators, we can actually say that we have the decomposition of V into, so let me write it as these cyclic spaces. So, which are some Z T V 1, direct sum etcetera, direct sum Z T V r. So, we have this cyclic decomposition of this capital V consisting of indecomposable T invariant cyclic spaces. Okay. So, what are these? So, these spaces, so they are indecomposable cyclic T invariant subspaces. So, this is what we get it in Jordan normal form. So, now if you think about it, so each one of them will corresponds to some Jordan blocks like lambda 1 comma n 1 and so on, some lambda r comma n r. So, now if we actually talk in terms of the Cx representation, it is easy to see that these components Jordan blocks that are appearing in the operator this decomposition. So, they are the indecomposable sub representation that we are interested in. Okay. So, it is clear. So, it can be proved using just cyclic decomposition theorem. So, we know already we have this decomposition. So, let us call it this is Jordan normal form. So, this is Jordan normal form. So, we have this Jordan normal form decomposition of capital V, which consisting of direct sum of this indecomposable cyclic T invariant subspaces. Since T invariant subspaces corresponds to Cx subrepresentations, so these cyclic subspaces must be exactly indecomposable subrepresentation. Okay, they can't be something else. So, note that the cyclic spaces appear in the Jordan normal form decomposition or the indecomposable sub representations that we get in the decomposition that we saw in the earlier theorem that we obtained in earlier theorem. So, basically the matrix of T with respect to that basis, whatever basis that coming from this individual Jordan blocks. So, that is going to look like the corresponding Jordan blocks J lambda 1 n 1, J lambda 2 n 2 and so on. So, now if we think about it, so there is this uniqueness involved in the Jordan normal form. So, up to permutation these Jordan blocks, so they are unique. Okay. First of all, their sizes are unique, and not only that, so up to permutation, so these Jordan blocks are unique. So, that is exactly answer to the question whether this indecomposable decomposition, so whether this is unique or not. Okay. So, this uniqueness question is answered. So, when we work with this CX modules using this Jordan normal form. So, you can already see that this is indeed a big result. Okay. First of all, getting the decomposition in a more algorithmic way, that is also very difficult. On top of it, we also wanted this uniqueness because they also like serve very important purpose in the computation. So, that is guaranteed using this existence and uniqueness of Jordan normal form. So, if we start using the representation theory language, we can see that just considering one simplest algebra, which is the commutative associative algebra generated by one variable x, already its representation theory is much more complicated. In simplest terms, that is actually we can say that the entire basic linear algebra course is about understanding the representation theory, finite dimensional representation theory of this one algebra CX. So, now what we want to do in representation theory, we want of course change these algebras capital A, and then we want to understand its representation theory. Okay. In this course, what we are going to do, we are going to focus on particularly the algebra coming from the finite groups, that is the group algebra CG. So, we take A to be CG, and then we actually try to understand finite dimensional representation of this algebra. So, that is how I am going to demonstrate the representation theory using this particular example, finite groups. So, as I said, in general it is very hard to prove uniqueness, but whenever you work with some nice algebras. So, for example, if we take CG with G being finite group, then one can prove that the category of finite dimensional representation, that is going to be semi-simple. So, if it is semi-simple, then we can use some ideas from linear algebra and so on, then we can guarantee this uniqueness. So, otherwise we have to use some tools like Jordan-Holder theorem for the other algebras. But anyway, we will not get into more abstract stuff in this course. We will just focus on this finite group representations and use some tools from basic linear algebra like inner product space and so on, and character theory in order to prove this uniqueness and so on. Okay. So, I will stop here. So, I will actually continue in the next class.